If you really want to build professional, robust, and resilient Java applications, you have to get a handle on the core engine that makes them tick. So today, we're diving deep into the 4 essential pillars that, honestly, separate the amateur code from truly professional software engineering. So here's our game plan. We're going to kick things off with how to handle stuff when it inevitably goes wrong. Then, we'll see how Java manages to juggle multiple tasks at once. After that, we'll explore how information flows in and out of our apps, and finally, we'll get into the tools for building really flexible, reusable code. This is your core Java toolkit. Let's get into it. All right, let's dive into our first pillar, exception handling. Because let's be real, in the real world, things almost never go exactly to plan, and your code absolutely needs to be ready for that. So what even is an exception? I love this analogy. Think of your application as a car. An exception isn't the car crash itself. No, it's that check engine light that suddenly flashes on your dashboard. It's a critical signal telling you, hey, something unexpected happened and you need to pay attention. You can't just ignore it and hope it goes away. You have to handle it to keep your whole application running safely. Now, in Java, there are 2 main flavors of these warning lights. On the one hand, you've got checked exceptions. Think of these like a mandatory pre-flight checklist for a pilot. The compiler knows that trying to read a file might fail. Maybe the file isn't there, so it forces you to have a backup plan for that I/O exception. On the other hand, you have unchecked exceptions. These are more like sudden, unexpected turbulence. They're usually just plain old programming mistakes, like the infamous null pointer exception. You know, when you try to use something that isn't actually there. They can pop up anywhere, and they're a dead giveaway that there's a bug in your logic. So how do we handle them? With this little safety net right here. The try, catch, finally block. It's super straightforward. In the try block, you put the code that might go sideways. If everything works, great. But if an exception gets thrown, the program immediately jumps down to the catch block. That's where you deal with the problem. And then there's the finally block, which is the really cool part. No matter what happens, success or failure, the finally block always runs. This makes it the absolute perfect place for any cleanup you need to do, like closing a file or a network connection. And this brings us to some really important rules of the road. First, be specific. Don't just catch a generic exception, catch the specific thing you're expecting. You should also use the modern try with resources statement whenever you can. It lets Java handle the cleanup for you automatically. And this one is huge. Never, ever use exceptions for your normal program logic. That's what simple if statements are for. Okay, pillar number 2. We're now looking at how Java applications can become master multitaskers, doing many things at once, and most importantly, doing it safely and efficiently. Let's talk about concurrency. The best way to think about concurrency is to imagine a factory. Each thread in your application is like a worker on an assembly line. Now, if you're the factory manager, your job is to make sure all these workers can do their jobs at the same time without, bumping into each other or breaking the machinery or just causing total chaos. That coordination, that's the heart and soul of concurrency. And this slide shows one of the biggest dangers in that factory, something called a race condition. This is a nasty, hard-to-find bug. Imagine 2 of your workers, 2 threads, try to update a counter at the exact same time. The counter is at 5, the first worker reads 5. The second worker also reads 5. They both add 1, and they both write 6 back. Whoops, the count should be 7, but it's 6. You've just lost data. The solution is to make that operation atomic, meaning it's indivisible. Using a special class, like atomic integer, guarantees that the whole read add 1 write back sequence happens as a single uninterruptible step. Problem solved. So a really classic way to get these workers to cooperate is the producer-consumer pattern. It's beautiful. You have one group of threads, the producers, who create tasks and put them on a shared conveyor belt. In Java, that conveyor belt is often a blocking queue. Then you have another group of threads, the consumers, who just grab tasks off the belt and process them. And the queue itself is the brilliant part. It handles all the tricky coordination for you, automatically pausing producers if the belt gets too full and pausing consumers if it's empty. So the bottom line here is to use the modern, high-level tools Java gives you. Seriously, don't create threads by hand anymore. Use something called an ExecutorService. Keep the parts of your code that are synchronized or locked down as small as humanly possible. And here's a pro tip. Whenever you can, use immutable objects. I mean, if the data can't change in the first place, you don't even need to worry about protecting it. Okay, so our application can handle errors, and it can run multiple tasks at once. But how does it talk to the outside world? That brings us to our third pillar, Java input and output, or just I/O. At its core, I/O is all about streams. The easiest way to picture it is to think of them as pipes. Data flows through these pipes into your application when you're reading something, and it flows out of your application when you're writing. This data can be raw bytes, like for an image, or it can be a stream of characters, like for a simple text file. Now, Java's I/O libraries have had a pretty serious glow-up over the years. The original java.io package, well, it worked, but it could be a little clunky. The modern java.nio package, especially the update called NIO.2, is a massive improvement. It gives us these powerful, much more intuitive tools like files and path that make doing common file operations an absolute joy. So let me hit you with a classic real-world problem. You've got a log file, and it is 10 gigabytes. Huge! You need to process it somehow. Now, if you try to just read that entire file into memory at once, boom, your application is almost certainly going to crash with an out-of-memory error. So what do? And the solution is just beautifully elegant. You don't read the whole file. You stream it. Modern Java lets you treat that massive file as a continuous flow of data, and you process it line by line. This means your memory usage stays incredibly small and totally constant, whether that file is 10 gigabytes or 10 terabytes. It is an absolute game changer for working with large data sets. For our final pillar, we are looking at two features that completely changed how we write modern Java: generics and lambdas. These are the tools that let us build code that's flexible, super safe, and way more expressive. Generics are basically just templates for your code. So instead of making a special box just for strings and another special box for integers, you just create one generic box T, where T can be any type you want. Think of it like a bakery box. It can hold any kind of pastry, but you put a label on it, donuts or croissants. And that label makes sure you don't accidentally mix things up. That's what generics do. They give you that safety check before you even run your code. And this slide right here perfectly captures why that's so powerful. In the bad old days before generics, you just get a generic object back. You'd have to manually cast it and just hope you guessed the type right. It was a huge source of crashes at runtime. But with generics, the type is part of the deal. There's no casting, no guesswork, and if you try to put the wrong thing in the box, the compiler catches it for you instantly. So much safer. Now let's pair generics with lambdas, which are just these tiny lightweight functions. Look at how clean this is. We start with a list of names. Then we use a little lambda expression to filter that list, keeping only the short names. Next, we use a method reference, which is just a super clean shortcut to transform each of those names to uppercase. And finally, we collect the results into a new list. It's like building a little data pipeline, and it's so clear and readable. So, just a few key takeaways here. First, always specify the generic type. That's where all the safety comes from. Second, keep your lambdas short and sweet. If the logic gets complicated, pull it out into its own named method. And definitely embrace method references whenever you can. They often make the code even cleaner. So, we've looked at the 4 pillars that really make up the core engine of Java. We've seen how to handle errors, juggle tasks, move data around, and write flexible code. So, what's the big picture here? What's the main takeaway? And this is the most important part. These are not 4 separate, isolated features. They are a deeply interconnected toolkit. You'll use Java I/O to read a file, which might throw a checked exception that you have to handle. You might decide to process that data across multiple threads using concurrency, and you'll probably use a flexible data structure built with generics to hold the results. Mastering how they all work together is what takes you to the next level as a software engineer. And really, that's what this is all about, building software that's bulletproof. So as you start thinking about your next project, ask yourself, where can I apply these pillars to make my code more robust, more efficient, and more professional?